Welcome back. Today on the video we're gonna look at the second principle of thermodynamics. Okay, so let us recall first, recalling the first principle of thermodynamics, which is what? Q minus work was equal to the change in energy. Okay? So this is the first principle of thermodynamics. But what's important over here is to realize that really the figure for this is that, let's say we have a hot reservoir over here. Okay, this is Q. Alright, so we do a power cycle, and this will generate power. So since I mentioned power cycle, let's maybe be more precise. So what is a power cycle? If this is the temperature and this is the volume, or the specific volume, most cases would be something like this. Okay, so this is for a power cycle. Alright, so for the power cycle, we know that D is a change in kinetic, potential, and internal energy. But if we start at one location, we end up to the same location, we could say that the overall change in energy will be zero. In such case, what do we have? We have that all the heat could be transformed into work, or all the heat transfer could be transformed into heat power. So I think it's easier to understand these ways the limitations of the first principle. So basically what it means is this: you can transform all the heat into power. Okay? But we know that is not possible because you always have losses. And why do we have losses? Because any type of engine, here's a power engine, but could be a refrigeration or heat pump, always operates between a hot and a cold reservoir. So let's call this one Q cold, and let's call this one Q hot. Okay? And the amount of work you can get out of this is equal to Q hot minus Q cold. So in other words, the first limitation is what? Any cycle or process, or any cycle process cannot be 100% efficient because the cycle or process always operates between two temperature reservoirs. So obviously the only case that this will be true will be if you are able to get here the absolute zero. Okay, but again, that's not possible. So that's one of the limitations. The first one is that with the first principle of thermodynamics states that any process or cycle is for which the change of energy is zero is 100% efficient. But we know that that is not possible in 99.99% of the cases, because any power cycle, heat pump cycle, or refrigeration cycle will always operate between two temperature reservoirs. So we need then to define something that is called the COP, coefficient of performance. Okay, in order to go against this limitation. So for example, for a power cycle, which figure is right here, but let me just redo it very quick. So what is the function of the power cycle? Obviously, is to generate work or power, always operating between a hot and cold reservoir, so it gets hot from heat from a hot reservoir and remove heat to a cold reservoir. So again, the COP or performance for the power cycle will be equal to what? And generally the definition will be what? What does this cycle needs to accomplish, and what do you need to do in order for the cycle to be able to accomplish? So what are we getting out of this one will be work. That's the purpose. Why do we need to put on heat? So this is equal to QH minus Q cold divided by Q hot equal to 1 minus QC over Q hot. Okay? And I can mention it now or maybe later, but basically if the system, that's what we use for the division of the entropy, and if the system is reversible, this should be equal to what? TC over TH. So this is basically the coefficient of performance for a power cycle. Okay, so the first limitation of this one is that really we cannot transform all the heat into work. Okay, all the work can go back into heat. So in order to resolve that issue, we define the coefficient of performance. So here I did the coefficient of performance for the power cycle. Now we're going to look at the refrigeration cycle. So we follow exactly the same process. We do a little figure. This will be refrigeration. Okay. So in this case, what is the goal of the refrigeration cycle? Is to put cold into the system from a cold reservoir. And then this will remove heat into a hot reservoir. So in order to accomplish this, you need to provide work or power to the system. So here is that, what are we trying to do over here? To put cold in the system. So we have Q cold. In order to do that, what do we need to do? Put power. So basically this will be equal to QC divided by Q hot minus Q cold. And if the system is reversible, this should be equal to Tc Th minus Tc. Okay, and finally something similar for the heat pump. Cycle. So basically we need exactly the same figures over here. But again, now what is the goal is to remove heat from the hot reservoir. This requires work or power. And we have again this cold reservoir over here. So now, the only difference with the previous one is that the coefficient of performance will be what? What are we trying to achieve over here? To remove heat. In order to do that, what do we need to do? Put work or power. So this will be Q hot divided by Q hot minus Q cold. Or this will be equal to T hot minus T cold. Okay, now let me just rewrite this equation over here. Okay, so we call in the equation we had before, Q equal to other work. This equation, the equal sign, actually means what? That you can read it from left to right or from right to left. So that means that you can transform other heat into work, or you could transform other work back into heat. But we know that that is not always possible. So basically, this equal sign means that the process is what? The assumption you make over here is that the process is reversible. Okay, and the example I'm going to give next is not really correct, but is good for the understanding, okay? So basically, let's say you have water, ice. The ice, without any action, you can get to liquid water, okay? And then you could go back to liquid water to ice. So this system will be reversible. It's just an example. It's not really correct, but as example. However, you can have another process in which you burn a piece of wood or a log of wood, and what's going to happen, you're going to get ashes, but then you cannot get the wood or the log of wood from the ashes. So that one will be irreversible. Okay? So the second limitation is that the first law is not able to define if a process is reversible or irreversible. Again, the example is not really correct mathematically, but it's good for the explanation. So the second limitation is that first principle, cannot predict if a cycle or process is reversible or not. Okay, so the first principle cannot do it. However, what did we define on the previous chapter? We defined the entropy. So what was the entropy? We defined the entropy as change in entropy is equal to delta Q over the temperature. And we say what? That if a delta S or delta Q over T was equal to 0, the system was reversible. And we say that if this was actually higher than 0, the system was said not reversible or irreversible. So what is the solution for the first principle of thermodynamics to become this problem of reversible or irreversible? Actually, it would be to combine these two equations. Or more precisely, really the full definition for the first principle. Okay, so to overcome this problem, we're going to say over here, recalling again. So the first principle of thermodynamics, what? Q minus work equal to change in energy. And let me just rewrite this really as delta Q minus delta W equals to dE. I know we use this one all the time, but this one is really more correct. I use that one because it's the one used in most textbooks. And then the second equation we have is that the entropy, so delta S, so let me just call it ds, will be equal to delta Q over T. So you see that from this second equation over here, you could rewrite delta Q equal to T ds. So in such case, if we substitute this over here, what do we have? So substituting, you have that delta Q minus delta W equals dE will be equal to what? T ds minus partial W will be equal to dE. Okay? Or you can write it as T ds minus work equals to dE. So either one is correct, but this is the one you're going to find most commonly in books. But this is really the one is more correct, and that's probably the one I'm going to be using from now on. Okay? So now basically, this equation here, this is the second principle of thermodynamics. Okay, after this, I'm going to derive, but really it's the same thing, what is known as the TDS relations, which basically is just to take this equation and rewrite it into a different form for a closed system or an open system, or for internal energy or enthalpy. That's basically what we'll be doing, but we'll do that on the next video. Thank you for your attention, and have a great day.